Good morning. Today I'll introduce a new chapter on CFD and turbomachinery. I'll be in brief, and this is the part 1 of the lecture. I have presented here a picture which is the result from an alias. Here, the wake from the upstream row of blades are passing through the downstream blades, and thereby the wake has been distorted within the blade passage, forming the small-scale eddies, which are resolved by alias. Thereby, the alias here is successful to resolve the turbulence and the flow field, three-dimensional flow field that appear within the blade passage. And this wake will interact with the boundary layer forming of the suction surface, and thereby the periodically excites the boundary layer. And this kind of flow is called wake-induced flow. So here the flow is highly unsteady and three-dimensional. So thus, with this picture, which is a motivating one, I'm starting the chapter CFD applied to turbomachinery. Contents of the lecture are Introduction to CFD, Governing Equations, why CFD is needed, what is the role of CFD in fluid mechanics, errors and uncertainties, different schemes and the formulations. After this, I'll discuss the application of CFD to turbomachinery. I'll now discuss about governing equation of fluid flow and heat transfer. The fundamental equations of fluid mechanics and heat transfer are derived from conservation of mass leading to continuity equation, conservation of linear momentum, that is referred as momentum equation, and momentum equation comes from Newton's second law, and then conservation of energy, which is derived from first law of thermodynamics. This lead to the differential or integral forms of equation describing the physics involved in fluid flow and heat transfer. Now I should explain the assumption involved in deriving this equation. The assumptions are: a fluid is considered an isotopic and Newtonian substance, that is, it obeys Stokes' hypothesis. A fluid is said to be isotopic when the relation between the components of states and rate of strain is same in all directions, and this relation, if it is linear, the fluid is called Newtonian. Furthermore, we'll regard the fluid as a continuum substance. Furthermore, the equations are derived here following the Eulerian approach. Thus, the assumptions are: the fluid is considered here isotopic and Newtonian. It is considered as continuum, and the equations are derived following Eulerian approach. In the Eulerian approach, all fluid's properties are described as a function of space and time. That is, I have indicated here density, pressure, velocity components, and temperature can be expressed as a function of T, X, Y, Z. T stands for time, X, Y, Z represents the position. Now I'll describe the equation of motion. I'll initiate with the continuity equation. The continuity equation can be put in the conservative form and non-conservative form. In the conservative form, the equation is del rho del T plus del dot rho V is equal to 0. Now here let me define velocity vector V is equal to I into U plus Z into V plus K into W. I, J, K be the unit vector in X, Y, and Z direction, and U, V, W be the component of velocity vector V in X, Y, Z direction. Similarly, the operator del, that is vector operator, is represented as I into del del X plus J into del del Y plus K into del del Z. So I have defined here del. So let's come back. This is the equation which is the conservative form. Del rho del T is the local change of density. Now in non-conservative form it would be d rho dt plus rho into del dot V is equal to 0. D rho dt represents the total change, that is local change plus convective change. Now for incompressible flow, when density remains constant, then this above equation number 2 becomes dV, that is del dot V is equal to del U del X plus del V del Y plus del W del Z is equal to 0. This is the continuity equation for incompressible flow, that is equation number 3, which represents dV is equal to 0. Let me discuss in brief about the momentum equation. The basis of the momentum equation is Newton's second law, that is F is equal to M into A. M is equal to mass of a fluid particle and A be the acceleration, where E can be given by dV dt, that is the total acceleration, would be equal to del V del T, that is the local acceleration, plus V dot del V, that is convective acceleration. Now, applying Newton's law on a moving element, we have the momentum equation for a unit volume as rho into dV dt is equal to x plus s, where x is the body force and s is the surface force per unit volume of the element, fluid element. Thus now we must distinguish here two types of forces on the fluid element, which I have told as surface force and the body force. The surface force can be considered as pressure force or the viscous forces, and the body forces can be considered as gravity force, centrifugal force, coriolis force, electromagnetic forces, and so on. Thus, from here, the equation 5 gives us the momentum equation per unit volume. Here I have presented the momentum equation in non-conservative and conservative form. When the equation is put to the non-conservative form, it is given by rho dv dt is equal to rho within the bracket del v del t plus v dot del into v is equal to minus del p, that is the pressure force, plus del dot tau ij, that's here, plus rho into g, that's the body force. Similarly, the momentum equation in the conservative form is del rho v del t plus del dot rho v into v is equal to minus del p plus del dot tau ij plus rho g. That is equation 6 and equation 7, where tau ij, that is the stress, can be shown as mu within the bracket del ui del xj plus del uj by del xi minus 2/3 del ij del uj del xk, where del ij is the chronicle delta. That is equation number 8. So this is the momentum equation in non-conservative form, equation 6. Momentum equation in the conservative form, equation 7, where the expression of stresses is given by equation number 8. Now, considering the energy balance on a fluid element, one can derive the energy equation, which can be given by del T rho capital E plus del xj rho E plus P into uj plus del xj tau ij into ui, that is work done because of stresses, plus del qj by del xj is equal to 0. This is the heat added to the element. Now, where the heat flux vector can be given by qy is equal to minus mu cp by pr into del t by del xi. Now, the pr is the Prandtl number. Now, where the internal energy capital E is defined here as E is equal to CVT plus half uy. CVT can be represented as small e, that is internal energy, plus half uy. That half uy represents the kinetic energy of the element. Now, the perfect gas equation of state is considered to be applicable here. That is, P is equal to rho RT. The following are the relations for a perfect gas equations. E is equal to CBT, E being the internal energy. H is equal to Cp into T. H stands for enthalpy. Gamma is equal to Cp by Cv. And R equal to Cp minus Cv. Thus, we can write Cv is equal to R divided by gamma minus 1, and Cp is equal to gamma R divided by gamma minus 1. For air, gamma is equal to 1.4 and R is equal to 287 meters squared per second per K. Thus, the perfect gas equation becomes P is equal to gamma minus 1 into rho into small e, and T equal to gamma minus 1 to small e divided by R. Furthermore, the laminar viscosity or the coefficient of viscosity mu is assumed here to be a function of temperature only and is evaluated following Sutherland's law, which is given by mu is equal to Cu1 T to the power T by 2 divided by T plus C2, where C1 and C2 are constants for a given gas. For air at moderate temperatures, C1 is equal to 1.458 10 to the power minus 6 and C2 being 110.4. Thus, for air, one can evaluate mu as a function of temperature. The Prandtl number PR is equal to mu Cp by K is often used to determine the coefficient of thermal conductivity K once coefficient of viscosity mu is evaluated for a given temperature T. Furthermore, please note that analytical solution of this equation exists only for some simplified low Reynolds number flows. Thus, numerical solutions of Navier-Stokes equations are pursued for solving practical problems. As an example, I've stated here the governing equations for incompressible two-dimensional Newtonian fluid with constant properties and no heat generation. Thus, the continuity equation would be del U del X plus del V del Y is equal to 0. That's equation number 12. X momentum here is given by del U del T plus U into del U del X plus V into del U del Y plus 1 by rho del P del X is equal to nu into del 2 U del X2 plus del 2 U del Y2. Thus here, please note that this is the local change, this is the convective change, this is the pressure term, and this is the viscous term. So equation number 13 represents the X momentum. Similarly, Y momentum is given by del V del T plus U into del V del X plus V into del V del Y plus 1 by rho into del V del Y plus nu into del 2V del X2 plus del 2V del Y2. That is equation number 14. The energy equation can be written here as rho into Cp del capital T by del T, that's the local change, plus U del T del X plus V into del T del Y, that's the convective change, plus K into del T del 2T plus del X2 by del X2 plus del T del 2T del Y2. This is because of conduction, and mu into phi is called viscous dissipation term. So in the energy equation, this is the local change, this is the convective change, this is because of conduction, and this is because of dissipation, where the dissipation term can be stated as phi is equal to twice within bracket del u del x square plus del u del y square plus del u del y plus del v del y whole square. So that is equation number 16. Thus, x momentum is given by equation number 13, y momentum equation number 14, energy equation is given by equation number 15, and the viscous term is given by equation number 16. Till now, I have presented the governing equation of fluid mechanics and heat transfer. To a beginner dealing with computational fluid dynamics, there might be several questions in his mind. Why CFD? And what for? What are the roles or functions of CFD in fluid mechanics? What are the errors and uncertainties? What are the different schemes? Now I'll answer some of these questions in brief so that one can appreciate computational fluid dynamics in practice. In response to the questions, why CFD? I'd like to say that in CFD we deal with fluid dynamics equations that are based on conservation of mass, conservation of momentum, and conservation of energy, leading to the Navier-Stokes equation. These equations are nonlinear, second-order coupled partial differential equation. And the analytical solution of these equations is not possible. Thus, the prime aim of CFD is to solve this equation numerically. Computational fluid dynamics, what is it? In response to the questions, I'd like to say that CFD is the art of replacing the governing partial differential equation of fluid flows with numbers and advancing these numbers in space and time to obtain a final numerical description of the complete flow field of interest. The instrument that allowed practical growth of CFD is the high-speed digital computer. Now, to give the numerical description of flow field around an aerofoil, here we'll have to first consider the domain and mesh. So what is domain and mesh? A domain is the portion of space around the body where the CFD simulation is conducted, and the computational domain needs to be discretized into a computational maze or grid to solve the discretized equation of fluid flows. Thus, we solve the discretized equation of fluid flow for points within the mesh if we consider the cell-centered scheme. We'll evaluate variables, fluid variables, at the center of each mesh to describe the flow field numerically around the body of interest. Here I like to refer the remark of J.D. Anderson in 1991 to explain the role of CFD in modern fluid dynamics. CFD can be viewed as a third dimension in fluid dynamics. Here I have given a sketch. CFD supports and complements both experiment and the pure theory. Furthermore, I'd like to add that CFD is not a passing fad. Rather, with the advent of high-speed computers, CFD will remain the third dimension in fluid dynamics of equal stature and importance to experiments and theory. Anderson, 1991. Modern CFD versus wind tunnel experiments. While comparing CFD results with tunnel experiments, definitely the question arises about the quality of CFD results. What are the uncertainties? Yes, there are uncertainties and error in CFD calculations. Errors are due to the physical model incorporated in calculations, such as in turbulent flows and in chemical reactions. There are approximations. Furthermore, in any numerical scheme, there are truncation errors associated with algorithms, round of error, and so on. Thus, one can appreciate that there are uncertainties in CFD calculations and thus the results. Despite of these uncertainties and drawback, the results of CFD are amazingly accurate for a large number of applications. What can CFD not do? It cannot produce physics that are not properly included in the formulations of the problem. That is, while dealing with turbulent flows, the model are nothing but approximations of flow physics. Thus, they cannot produce the accurate result. There would be some inaccuracy involved. Similarly, the chemical reactions, boundary conditions. So, turbulence and chemical reactions are open area of the present day research in CFD. This is the time to discuss about the numerical methods, that is finite volume versus finite difference schemes, what is explicit and implicit formulations, and the nomenclature, how the cell and nodes are defined. So I'll go to the next part, that is the second part of my lecture about formulations and numerical schemes. I have explained the numerical procedure with the help of a flowchart or the flow diagram. What I have written here, that in CFD we deal with the conservation laws of fluid mechanics. Now this governing equation can be put in the differential form or integral form. As an example, I have taken the continuity equation. In the differential form, it will be del rho del t plus del dot rho v is equal to 0. And in the integral form, it will be del t volume integral of rho into d omega plus surface integral of rho v dot eta into ds is equal to 0. This surface integral, which is integral of rho v dot eta into ds, represents the total flow flux out of the small volume omega. So this is the integral form of continuity equation, and this is the differential form of the continuity equation. When you use the differential form, the domain needs to be divided into discrete points, and we'll solve discretize differential equation for these discrete points that will land to finite difference method. On the contrary, when you use the integral form of the equation, the domain would be divided into discrete volumes for three-dimensional form or area for two-dimensional form. These volumes or area is referred as element for finite element method or cell for finite volume methods, and we'll solve the discretized integral equation for this elemental volume, leading to finite volume scheme or finite element schemes. Thus, here I have explained what is the difference between finite volume method and the finite difference methods. I will explain now about finite difference versus finite volume method, that is FDM versus FBM. We know that in finite difference method, partial differential equation of fluid flow would be used. That is, the equation will have terms like del u del x, del v del y, del 2u del x2, del 2v del y2, and so on. Considering a rectangular grid at a point, if I approximate del u del x, it can be represented as ui plus 1j minus uij divided by del x. So this is the finite difference form of the term del u del x at point ij in the rectangular domain. Finite difference form of a governing equation is referred as finite difference equation FDE. Thus, the primary objective of a finite difference method is to convert PDE to FDE for a given rectangular domain. To explain this, let me consider a rectangular mesh. So I'm drawing here a mesh which is rectangular. Have indicated a cell being a finite volume. So I have indicated a cell, and I'm considering this scheme as a cell center. That means center of each cell, I will store the variable and update that. So all centers of different cells in the maze I have indicated by cross. And let us consider the center which has been marked by I hatched, which is actually the ij cell. Hence the center is represented as ij. This is the indices of the center of the cell which has been hatched. Now right side cell center would be represented by I plus 1j, and the left one would be represented by I minus 1j. Similarly, the center which is just top of the middle one would be represented as I and j plus 1, and the bottom one is I G minus 1. So this I plus 1J, I minus 1J, they are called the indices of the cell. Now for a structured maze, which is represented here, the cell and the nodes are explicitly defined. Here the nodes is the point where the variable would be stored. In this case, the center is the node. So please note that for structured maze, cell and nodes are explicitly defined. Thus, for this rectangular maze, for a given differential equation, I'll first discretize the equation and create the finite difference form, and then with some numerical methods I would solve this finite difference equation, and thereby I would evaluate the variable at every point which is denoted by the node for a given maze. Now another question may arise: what will happen when the body is not conformal to rectangular maze? Suppose, let me consider an aerofoil, right? Or a cylinder. So suppose if you are asked to evaluate or assess by finite difference method flow around an aerofoil or flow around a cylinder, then what you will do? How would you assess? Let me consider a grid on an aerofoil. Or on a cylinder. Is the maze. Now in both cases, if you consider a cell, they are not rectangular. So on physical domain, you cannot apply the finite difference equation, or you cannot even form the finite difference equation. In those cases, what one should do? Yes, with some transformation, I'll map this physical domain to the computational domain. So if in the physical domain x and y be the axis, and the computational domain the axis would be psi and eta, and in the computational domain the grids are rectangular. So there are transformations where I can map the point in the physical domain to the computational domain and get it back. So what would be the result? The differential equation will be transformed from physical domain to the computational domain, thereby the governing equation now would be very complex, having some extra term, and then we discretize this transformed partial differential equation and solve by some numerical techniques. After solution, the variable in the computational domain has to transform back to this physical domain. Thereby, you appreciate here that using finite difference method for solving flow through a body, which is where the surface is curved, not rectangular, will have to go through some additional routes that transforming the governing equation to computational plane, solving those equations in computational plane, and then transforming the variable back to the physical plane to get the flow field. However, if you consider the finite volume or finite element method, this complexity would be removed. Here, we can solve the governing equation in physical plane. That means, suppose I am solving flow through a cylinder, then I'll, with respect to some axis, fixed axis, I'll develop the P, so I know the coordinate of each point. And then for a particular cell which has been marked here, which has been hashed here, for this cell, we'll do the conservation of equations to get the flow field. That is, now the integral equation will be discretized and will form a discretized version of integral equation. And then, with the help of numerics, we'll evaluate the variables in the physical plane only. Therefore, the very important point is that the finite volume technique can be carried out both in structured and unstructured mesh. Very important point. That is, in finite difference is valid for only structured mesh. Whether finite volume or finite element, we can employ any kind of mesh, whether structured, unstructured, rectangular, triangular, and thereby we can utilize the geometric flexibility, easily resolving the flow on a complex shape, on a body of complex shape. Thus, I have written here also that FDM method, finite difference method, is restricted for structured grid only, while finite volume method is valid for any kind of mesh. What I have explained so far, I have summarized under the title Physics of FVM. The discretized integral form of fluid dynamics equations, unlike the differential form, would be used in FVM, which is the basis of the method. Here the domain would be subdivided into small volume or area as in finite element method. In FBM, the term cell is used instead of the term element used in FEM. The conservation laws are applied to each cell to determine the flow variable at some discrete points of the cells, which is called node. The nodes could be cell center, cell vertices, or the midsides. The whole geometrical freedom of finite element method can be used in finite volume method. Here I have indicated the sketch of a structured quadrilateral grid, structured triangular grid, and unstructured triangular grid. So thus you are acquainted with now the structured and unstructured mass. I'd like to state here the two important points. One, the choice of the nodes can be governed by the wish to represent the solution by an interpolation structure, as we do in FEM. In the figure 2, I have indicated different orientations or combinations of cells and nodes. Suppose for cell centers and cell vertices, where the variable in one case are stored at center of a cell, and in other case the variable are stored at the vertices of the cell. In both the cases, we need some interpolation function to evaluate fluxes at the surface of the cell, which has been indicated by hatched. So in this figure, A and B have indicated node and cell. That's why I like to repeat here that in both the cases, that is cell center and cell vertices, here we need an interpolation function to evaluate the fluxes at the wall of the cell. However, we can define our node and cell in such a way that such an interpolation function may not be needed. Thereby, I have written here the point number 2 as, in FBM, a function space for the solution need not necessarily be defined, and the node can be chosen in a way that does not imply an interpolation structure. Suppose if we consider the structured grid where rho, P, T, temperature are stored at the center of the cell, while U, V are stored at the surface of the cell. By this staggering, we can eliminate actually the need of an interpolation function to evaluate fluxes at the surface of the cell. Similarly, I have indicated here a non-staggered overlapping cell. Note that the hatched portion is a cell, and these are the points, these are the nodes where variables are stored. By overlapping cells, we can eliminate the need of interpolation structure also. That is, FBM having one additional features that it depends on you how you choose your node and cells, and by that way you can eliminate the need of interpolation function or structure to evaluate fluxes at the surface of the cell. By referring the non-staggered overlapping maze, I like to define here the volume, which is a finite space where the conservation of mass, momentum, and energy would be carried out. Thus, by decoupling the volume and cells, the freedom to determine the functional representation of the flow field in finite volume method becomes much larger than in finite element and finite difference method. Further, finite volume method tries to combine the best from finite element method, that is geometric flexibility, with the best from finite difference method, that is flexibility in defining the discrete flow field. However, finite volume has some difficulties in evaluating the derivatives, which will be discussed later. I'll explain here about FEM formulation. For simplicity, I have considered Euler equation. Thus, Euler equations in the vector form would be del u del t plus del e del x plus del f del y is equal to 0. That's equation number 17, where u is called the solution vector and e and f are called flux vector. The expression for u is given by rho, rho u, rho v, and rho e, while the expression for the vector e is given as rho u squared plus p, rho u v, rho e plus p into u. And while the expression for f can be given as same as e, where u has been replaced by v. Now, the equation 17 has been put to the integral form with the help of Green's theorem as del del t volume integral of u into d omega plus surface integral of q dot eta into ds is equal to 0, where q is given by e into ix plus f into iy, where ix and iy be the unit vector in x and y direction, omega be the volume of a cell, ds is the surface element. In case of two-dimensional, it will be a surface length, or for three-dimensional flow, it will be the area of a surface, and eta be the unit vector for a surface normal. Thus, eta into ds would be equal to dy into ix minus dx into iy. Now I'll explain a bit here. Now if I consider the equation 17, which has been put in the vector form, and I have given the expression for EU, U, E, and F. Now The first row represents the continuity equation. Second and third represent the x and y momentum, and the fourth row represent the energy equation. Let me explain further. If we expand the first row, what it will give? It will result to del rho del t plus del x of rho u plus del y of rho v is equal to 0. Thus, it's a continuity equation. Now, if I expand the second row, which is del t of rho u plus del x of rho u square plus p plus del y rho uv is equal to 0. So that is x momentum equation. Thus, if we expand the other two, one will give y momentum equation and the energy equation. Thereby, the vector form is a very compact form of representation. Now let's concentrate on the integral form. Now the question is how one can evaluate the surface normal. Let me explain that. Suppose let us consider a grid. And with respect to some coordinate systems, I know each points, the coordinate of each points are known to me. Now I have represented those points as 1, 2, 3, 4. So I have represented like in this anti-clockwise direction. Now for the surface 2 and 3, I'll evaluate eta into ds. How would I do that? Eta is the normal unit vector. So this is the eta, right? So I can calculate eta ds equal to as dy into I minus dx into z. Now what is dy? Dy can be evaluated as y3 minus y2. Right? I'm very sorry, it should be written as suffix, not superscripts. So this is 3 and this is 2. Similarly, dx would be equal to x3 minus x2. So now you know dy dx, and put the value of dy dx, you will get eta into ds. So what I would like to say that if one develop the grid, if they know all the coordinate points, then one can easily assess eta into ds for every cells, and thereby can do the operations q dot eta ds. And once you evaluate all those things, you can do the integration, numeric integration, following some algorithm. Now, the semi-discretized form of the equation 18 for a cell omega ij would be omega ij del u del t plus surface integral e into dy minus f into dx is equal to 0. That is equation number 19, where E and F can be defined on the boundary of a cell. For a cell-centered formulation, the simpler choice would be EAB is equal to half of E star ij plus E star I plus 1j. What does it mean? To explain that, I have considered a grid here. So I have shown the cell, which is the head portion. So this is, I have considered ij cell, and I know the vertices. So I have indicated the vertices as A, B, C, D. Thus, I have considered the fluxes at the surface AB is equal to half of the neighboring cell. That is why I have indicated here EAB is equal to half of E star ij plus E star I plus 1j. Star indicates the time level at which these values are evaluated. Similarly, if AB is equal to half of F star ij plus F star I plus 1j. Now, if all these quantities are evaluated at the old level N, then we'll line to an explicit formulation. And if all these quantities are evaluated at a new time level N plus 1, where the variables are not known, then we'll land to an implicit formulation. For implicit formulation, we need to invert a matrix, while for explicit formulation is simple to evaluate. Now, furthermore, I'd like to add that after evaluating the fluxes, now I'll put the value of fluxes in the equation number 19, either by implicit or explicit way, and then I need to integrate the governing equation 19 by some numerical technique. And then all the variable has been evaluated from the present time step N to the next time level N plus 1. And we continue this numerical integration till they converge for a steady system, or for an unsteady system will continue the integration till the dynamic steady state is reached. That means we'll get a believable solution, which is time dependent solution. I have cited here some examples. Let us consider first the explicit scheme. So all these formulations have been put in time-dependent form. Thus few known explicit schemes are Lax-Wendorp schemes in 1964, McCormack schemes 1969, Jameson scheme in 1981. All these schemes are very popular and they are being successfully used in turbomachinery applications. Here the spatial derivative are evaluated using the known condition at the old time level. Advantages are they are simple, easy to implement the boundary condition, easy to vectorize for multiprocessing application in HPC. Disadvantages are CFL restriction, that is, time limit with which these schemes will be integrated is severely restricted, and thereby a large time will be needed or large time iterations will be needed for a steady state solution. Furthermore, there will be oscillations in the resolved flow field with discontinuities. That means if there are shocks, then there will be oscillations. There are methods so that this oscillation can be eliminated. In this regards, I like to say the Jameson algorithm, which is very attractive if implemented with residual smoothing, local time stepping, and multigriding in the finite volume formulations, where CFL restriction can be broken, and even for 3-dimensional flow, the CFL can be raised up to 2.5, which is a big advantage. Regarding implicit scheme, one popular name is beam warming 1978. Please note that the unknown variables here are evaluated from a simultaneous set of equations. The advantages are larger time step and faster convergence. Disadvantages are the direct solution involves inversion of a block pentagonal matrix for 2-dimensional flow and heptadiagonal matrix for 3-dimensional flow. Hence, approximate factorization is employed to convert these to a block tridiagonal system, introducing some factorization error. Thus, in an implicit scheme, there would be some error because of approximate factorizations. Furthermore, I have indicated that the interpolation function would lead to a variety of numerical schemes. I have explained this in brief, stating that there are different ways to evaluate fluxes at the boundary of a cell, which lead to different numerical schemes. For example, apart from the cell center formulation, one may use the flux vector splitting to assess convective fluxes term at the boundary of the cell, and this lead to an R-point scheme, thus the flux vector splitting leads to the R-point scheme. Similarly, another choice is to go for higher order schemes. Thus, one can define the interpolation function based on his choice to arrive at different numerical schemes. Regarding treatments of derivative, again we can use the Green's theorem and thereby del phi del x at a point ij can be expressed as 1 divided by omega ij surface integral of phi into dy, and del phi del y can be expressed as 1 divided by omega ij surface integral of phi into dx, where phi must be defined at the boundary of a cell and a mean value between the two adjacent nodes is a simplest choice. Thus, if I explain further, let us consider a cell as denoted earlier is vertex point A, B, C, D, and this is the center of the cell ij. This right side would be I plus 1j. Therefore, for the face A and B, phi would be phi AB, B is equal to phi I plus 1j plus phi ij divided by 2. Thus, I have defined fluxes at the surface, and then I can calculate cyclic integral of phi dy or cyclic integral of phi into dx, and then evaluated del phi del x or del phi del y. Thus, I have discussed about different philosophy of CFD, staging on finite volume method, as in turbomachinery will prefer to use finite volume method because of geometric flexibility. In the next lecture, I'll discuss on assessment of CFD in analysis of turbomachinery. Here I have introduced computational fluid dynamics in brief, and also have discussed regarding finite volume methods, which will be applied in the next lecture for turbomachinery. Thank you for listening.